everyone. It's my great honor to be invited to this conference. And after all the talks about animal studies, I'm happy to give you first human studies. So my talk today is about the role of the motor simulations and entrainment in speech and music perception. And let's start from a script system. It's called Oracle Bone script from ancient China. And it's a hieroglyphic, so you can guess the meaning from the shape. Like maybe like this one is the arrow, this is bow. So this comes an interesting one. So here is one. The left side is shape representing ear, and on the right is two mouths or sometimes one mouth. So guess which action verb it represents? Take a guess. Conversation, similar, yeah. Action verb. So it's listen. Oops, listen. Okay, so it beautifully described how our auditory system and motor system interact during those speech listening activities. So as we know, during the speech perception, there is a phenomenon called perception by production, also called perception by action. And so by listening to the speech, not only our auditory system process the signal, our speech motor system actually actively predict the upcoming signals by providing those articulatory predictions. And such auditory motor integration facilitate our speech perception, especially in those noisy and uncertain listening conditions. And similarly, in music perception, there are strong auditory motor interactions, whether the motor system work as oscillators or provide those prediction signals. We both believe those auditory motor systems interact to enhance our temporal predictions and auditory music processing. So my talk today will focus on two parts. The first part is a motor simulation in speech perception, and the other part is a motor entrainment in music perception. So the first one is already published, and we know there are effector regions in motor cortex, whether it's sort of traditional, like Penfield's homologue, or whether it's a newly found, more symmetric ones pattern. But when we're looking at those lip areas and the motor areas, when we use TMS to inhibit those two regions, we found it will impair the perception of the dental or the labial phonies. So it means that those motor areas actually effect a specific contribution to the speech perception. And similarly, for the laryngeal motor cortex, we know it contributes to control our vocal pitch during we speak or when we're singing. And when we inhibit the right laryngeal motor cortex, it actually impairs the perception of prosodies. And we also know those areas controls lexical tone production. In Mandarin Chinese, there are 4 tones, which is flat tone, it's rising tone, and the deep tone, and the falling tone. And when the same syllables combined with different tones, it represents different meanings. Like we know, like ma is mother, ma is horse, and another one is 水饺 means dumpling, 睡觉 means sleep. So guess whether baby wants dumpling or want to sleep. Take a quick guess. Like listen carefully. 水饺. It's dumpling or sleep? Dumpling. Oh, good guess. Yeah. So after my talk, I hope I can persuade you your motor system, your laryngeal motor cortex actually predict what's the pattern of the tongue. So my first question is whether the laryngeal motor cortex is engaged in speech perception in an effective specific manner, like the lip and the tone areas. And my hypothesis is the LMC, which is the laryngeal motor cortex, controls pitch contour and also the voicing of the consonant. So when they impair or inhibit these areas, it will impair the perception of the lexical tone and also the voicing of the consonant. And next, the second question is how bilateral motor cortex cooperate during those speech perception under varying listening difficulties. Like traditionally, we know the perception relies on left lateralized, but the speech production is more bilateral. So what's the contribution of the right hemispheres? And there are different hypotheses. According to the acoustic hypothesis, maybe the left one is contribute to consonant, and then the right hemisphere contribute to lexical tone perception. And according to the lexical hypothesis, maybe both the left hemispheres contribute to both perception types. And according to the motor hypothesis, maybe is more effector specific, and most importantly is the redundancy hypothesis. Like when we're listening in quiet, it's only the left hemisphere contribute, but when we're listening in noise, the right hemisphere will get engaged. So my third question is, what specific stages of this perceptual decision-making processes the bilateral LMC modulate? Like whether it's contribute to perception or it contribute to decision-making, and we think both processes maybe get involved for those motor areas. So the experiment is like we use it's a human TMS study. So we use offline theta burst stimulation, including also the inhibitory one and also the excitatory one. And we use it to modulate both the left or the right MC. And then the subject listen to those to do those categorical perception tasks on tom or on consonant, whether in noise or whether in quiet in different days. So we first localize our laryngeal motor cortex and also the tom motor areas as a control region by fMRI, and then we do the TMS study. And here is the results. So we first focus on the perception. So we use a slope of the identification curve to indicate the perceptual sensitivity, and we found the result is the inhibitory CTBS actually reduce the sensitivity of the consonant and the tom perception, which means that this area is causally involved in both the perception of the consonant and tom, and also the motor involvement is more left lateralized, and also when the task become more difficult with listening in noise, it increases the motor involvement. And next, we're looking at whether it also impairs the decision-making processes by looking at the RT distribution and also using the hierarchical drift diffusion modeling. And there are 3 parameters in this model. We know there is boundary, and also the drift rate, and also the starting point, which means that whether there is some response bias at the beginning of the task. And we believe they may influence both the boundary threshold by increase it or shrink it, or it may influence the drift rate by speed up or slow down, or it may influence the starting point by giving those response bias. And the results here is like when they use the inhibitory CTBS, it actually increases the reaction time across all the conditions, which means we need longer time to make the decision. And also it increases the boundary threshold, which means we have to accumulate more evidence to reach a decision. And also when we stimulate on the left hemispheres, it alters the drift rate. And also, when it also change the starting point, which means we give you more response bias, especially during those most difficult tasks, which is consonant in noise. So to summarize, this study suggests that bilateral LMC are causally involved in the perceptual decision-making of lexical tom and consonant, supporting the effector-specific motor hypothesis. And also, the LMC involvement is more left lateralized, and with the right regulation in noise, supporting the redundancy hypothesis. And also, the LMC contribute to various categorical decision processes, and depending on the stimulation hemisphere and also the task difficulties. So take-home messages, like when we say bilateral MMC may provide articulatory templates and especially motoric prediction or simulations to aid speech perception, especially for those degraded and adverse listening conditions. And this makes us to rethinking the current left lateralized dorsal string model of the speech perception. Maybe it's time to think about the right hemispheres. And let's move to the second part, and this is, I think, like this one more. So let's listen to some music first. I don't know how much of you like nod your head, tap your feet, okay, right? So it's very automatic to do the body synchronization. But and we already know the motor recruitment actually help us to refine those temporal predictions of the auditory pattern and also optimize the attentional allocation, like we pay attention to those those important time in those musical structures, and also improve the auditory perception. But we ask the question whether there are unconscious and implicit motor synchronization without our attention, without our consciousness. So we already know our cortical neural entrainment to those musical rhythm structures, whether at a note level or whether at the beat and meter level. And there is one pioneer study that showed that actually our oculomotor activity can track those higher order linguistic structures here. Like in addition to those neural oscillations, our like blink actually track those linguistic structures. So which make us to think, okay, whether those oculomotor activity, especially the blinks, can track those fundamental musical rhythms such as beat and without consciousness. So to answer this, we designed a study. We asked subjects to listen to 10 Bach chorales, which was highly regular beat structure. So here we have a note rate at 2.8 hertz, and the beat rate is at 1.4 hertz, and it's very regular. And we also have, this is original version, we also have a reverse version. We reverse order of the beat structure, so it keeps the same beat structure, but sounds unfamiliar. And we ask them to listen to for 3 times, and then at the end, you read how much you like it from 1 to 5, and we found there is no difference between those original and the reverse versions for the liking rate, and we recorded their EEG and also their eye movements simultaneously. So for the eye tracking, for the blink data, we actually do the Ballet codes and do the fast Fourier transformation to get the spectrum of this blink activity, see whether there is some spectral powers at certain frequencies, like here is whether it have the beat tracking. And for the EEG signal, we actually do the FFT as well to look at the neural oscillations, whether it can track the beat rate or the note rate. And we also want to know whether those two sources of data have some certain relationship. So we're looking at, we extract the EEG power at the beat rate, and also looking at whether they have the mutual information or temporal response frame with the blink signals. So here, so when we look at the blink activity, so when there is no music, the spectrum of the blink activity is flat, which means it's very blink randomly, right? There is no regular. But when music is on, you can see a very reliable and very strong peak at 1.4 hertz, which is a beat rate, which means that our blinks actually synchronize with musical beat without any consciousness. Like you never know, right? Your blink actually track those musical structures. And there is no difference between the original and the reverse version. And there's no correlation between this blink activity with the musical rhythm abilities. It's very strange. And we're also looking at the neural entrainment as well. We can see the clear peak at note rate and also the beat rate. And most importantly, there is a strong correlation between the blink and the EEG activities. So which make us wonder, those two sources of activity maybe have certain relationships. So we further investigate this by using mutual information. So we found that there is strong mutual information between those two signals, and it actually increased with repetition. And also there were stronger mutual information for original than reverse versions. And next, we also use temporal response function encoding model for someone not familiar with this technique. So we treat the blink onset as a stimulus and the EEG power at the beat frequency as a neural response. So we calculate the temporal response functions in these processes. And we found that actually the time point of zero, the time point of zero is the blink onset. We can see our neural response to the beat rate actually is time locked to the beat onset. And also, most importantly, like we found this neural activity gradually precede the blink onset across the first to third repetition, which means that there is a learning processes. So there were refinement of those neural predictions for the upcoming blinks through those shorter exposure. And there is also individual difference in this blink and the neural synchronizations. I just said this not relate to their musical ability, but here we found those two synchronizations is related to those white matter structures, microstructures. Like here, the blink synchronization was negatively correlated with the NDI of the left SLF, and the neural entrainment was negatively correlated with the NDI of the left AF, so which means that those white matter pathways connecting in the motor area and auditory areas actually contribute how well we can synchronize with musical beat structures, either by our neural oscillation or by our blinks. So that's why we have established the blink synchronization corresponds to neural entrainment to beat, and also we found this phenomenon transcendence mirror passive reflex to sensory stimulations, because those blink and the neural oscillations is modulated by experimental factors like the repetition and the reversal manipulations, and according to either like predictive coding and active thinking or the ASAP hypothesis, our finding actually suggests that those neural entrainment also contribute to the predictive timing of the blink activities. And next, we want to know, okay, we found a new phenomenon, so what's the boundary of this phenomenon, whether it depends on musical tempo or depending on the melody. So we did the second experiment. In this experiment, we have 3 tempos, from slow to medium to fast tempos, and we also have pure tone conditions, so we replace the notes, musical notes with pure tone sequence, so maintaining the same rhythm as the original ones. So here is the result. So regardless whether they have the melodic cues and of course the whole range of the tempo, we found significant those new blink synchronization phenomena. So it's very robust. And next, we want to know, okay, so it's a new phenomenon. What's the function role of this phenomenon? Why we have to blink to those musical beat structures? And we guess maybe it's related to dynamic attending processes. Like when we're listening to music, we pay attention rhythmically to those most important time point. Here, in this case, is a beat boundary. So, and also, it may guide our rhythmic sampling of the environment, maybe even cross modality. So to answer this question, we did the other 2 experiments. So in experiment 3, it's auditory target detection task. So we put some overtone on those on-beat time point. Your task is to detect those overtone as soon as quickly as possible. And our hypothesis is here: if someone can use their blinks to synchronize with the musical structure better, they can better detect those overtone detections task. And next experiment is a visual target detection task. So here, when we're listening to music, we present those red circles either on beat or off beat. So your task is just detect those visual targets. It's very easy, and just ignore the music signals. So for the experiment 3, we found there is still strong blink synchronization, and those blink activity was actually significantly correlated with detection accuracy of overtone, which means that those blink synchronization facilitate those pitch detection task, which means that we actually, like if we use our blink to synchronize to music structure, we can better detect those deviant on those important time point, which is a beat boundary. And the next experiment is very out of expectation. So in this visual task, we found there's no blink synchronization, which means that even this phenomenon is spontaneous, is without conscious, but is actually influenced by auditory attention. We have to actively listening to music. We can observe this blink synchronization. Once we drift our attention from auditory modality to visual modality, this phenomenon disappears. And also, we found there is a significant difference between the reaction time for the onset, for the on-beat and off-beat signal. So even the reaction time is even faster for the off-beat, which is out of our expectation. Actually, so we interpret that maybe when we're listening to music, when we do this task. For those time points around the beat boundary, maybe our attention was driven by the auditory system by the music structure, more dominant by those auditory modalities. So for the on-beat signal, it's even harder to be detected. But in contrast, for those off-beat signals, it's more likely to allow us to apply those flexible attention allocation. So conclusion here is we found those peripheral ocular motor activities, especially the eye blinking, spontaneously aligns with the regular musical beat during this active musical listening. This phenomenon we think is expanded the observed the behavioral repertoire associated with musical perception and auditory motor synchronization. And not only our brain oscillations, our bodies, and also our eyes actually proactively anticipate those upcoming events and synchronize with musical rhythms. This actually serves to aid our auditory sequencing and temporal predictions. And this blink synchronization corresponds to dynamic auditory attending and highlighting the role of cross-modal active thinking and embodied musical perception. So our future direction is maybe we change from regular rhythm to more complex rhythm like syncopations, whether this phenomenon still exists. And also we want to know how the blinks cooperate with other eye movements like the pupil size, and also looking at the neurocircuitry underlying this phenomenon. We know the basal ganglia, SMA, cerebellum is contribute to those auditory motor synchronization, but maybe frontal eye field is also contribute to this phenomenon. And there are also very clinical implications. Like we know deficits in reason processing is considered as a vulnerability in neurodevelopmental disorders like the speech disorder, ADHD, ASD. And this paradigm developed by listening to music and look at your blink synchronization is very fast, only takes 3 minutes, and is very easy to operate, and it's implicit, no task requirement. So maybe it's very useful for populations like infants and children who cannot actually do the finger tapping task. So the take-home message is when we're listening to music, we not only use our auditory system, but also our motor system. But in addition to the finger and the feet, we also use our eye movements to synchronize with musical structures. And this auditory motor synchronization facilitates those temporal predictions and also apply to our dynamic attending and proactive sensing to optimize information processing and also guide the rhythmic sampling in our environments. So yeah, thank my group and thank all the grants, and I will take your questions.
Yeah, thanks a lot for this very interesting talk. I think there may be questions. You go with a cue.
Thank you, that was very interesting. Regarding the synchronization with the neural EEG data, how do you know that it's not like a byproduct of motor activity?
Yeah, it's a very good question. We actually use, let me take you this one. Yeah, we actually use MSCCA to extract the component related to eye movements and remove those eye-related artifacts to clean up the EEG signal. So we think the EEG and the neural entrainment to the blink is not contaminated by those eye movements.
Thank you for the very interesting talk. I'm curious, what kind of instruction did your participants receive with respect to the eye blinking measurement gear? Were they specifically told that we're interested in how often you blink and how regularly you blink?
No. Yeah, we just ask them to listen to music, and after the end, rate how much you like it. Yeah, and at the end of the experiment, we ask them whether you notice your blink activity actually have a certain pattern. They say no, nobody has noticed that. Like when you listen to music, have you actually realized your eye movements is tracked in the musical structure? I don't think anyone realized that. Yeah.
Cool, thank you for a really interesting talk. I have a slightly, I guess, provocative question in the sense that the way you interpreted your results is an active synchronization mechanism between the blinks and the music. But could it be that it's a passive consequence of the fact that we have to blink? So we have to choose where to time our blinks. And there's quite a big literature showing that we time our blinks in periods that are sort of less attentively or cognitively demanding. And it could be that the beat is that time because it's possibly the most predictable part within the signal. So you just end up blinking there because you have to.
Yeah, it's a very good question. Like, we have no direct evidence to support it's proactive and it's predictive, and but I don't think it's a byproduct of attention effect. But I know blink is related to a lot of like listening effort and attention, But I don't have a good answer. I have a good answer for this one, but it's a very important one. I have to find answers for that.
You hypothesized that the blink entrainment might be rhythmic sampling related, but then it fell apart in the visual target detection overlain on the music task. And of course, that visual target detection differed both that it was a visual target rather than an auditory target, and you also had both on-beat and off-beat targets, so the musical beat was less helpful than in the auditory one. And thinking about, I'm curious how you think about whether one of those factors is more important in explaining that difference, or if they both matter, and how this links back to the rhythmic sampling hypothesis.
Yeah, so here, actually our on-beat and off-beat visual targets was intermixed in one block, so it's very hard to predict. It's not regular pattern. I think that caused our result like pattern here. And about the rhythmic sampling, like when we're listening to music, I think it helps us to guide our attention allocation. Like maybe we pay attention more to those important time points, especially those boundaries. So this may help us to also sampling the environment even across modalities, I think.
Thank you.
Okay, we have one final question. I'll try to throw it.
It's broken.
Thank you so much for the talk. I was curious, it was funny you mentioned you're the human person and amongst all the animal models today. To sort of ask a question about evolutionary tracking then, where do you think this kind of synchronization arises from? You know, there's a lot of like evidence of animals sort of having very rhythmic singing and stuff, but do they necessarily have connections to these kinds of things?
Yeah, it's a very good question as well. Like they would really want to looking at those neural circuitries, like especially basal ganglia and also the SMA premotor cortex. And by here, like as we already know, the eye blinks track those signals. We propose maybe those frontal eye field also contribute to the circuitry.
So then do you think like the evolution of the frontal eye fields is sort of aligned with these things, or the basal ganglia being
like
sort of
maybe like the frontal eye field is not guide only our view sampling. Maybe it's also guide our auditory sampling.
So one very last question.
Thank you for the interesting talk. This is maybe a quick one. I was just curious if you found any like you showed that the pupil, or not the pupil, the blinking matches the beat rate of the music, but did you actually look at if there's any features in the music itself that tracks, or well, that the blinks are tracking some particular feature in the music in terms of phase?
Yeah, no, we're only looking at this spectrum here, like to get those evidence. But we do analyze those acoustic features or even those musical structures of the sound, but have no relationship with the blink activities.
Oh, interesting. Thank you.
Thank you. Thanks again, the speaker. Yeah, and we
Okay,
move on
thank
to the
you
next
all.
speaker.